this module is on structural strengthening and stabilization, and in this there are 4 lectures planned in this. The first one is on load effects and introduction to strengthening and stabilization. Yeah, this is the outline. In the first one we will look at or in this lecture we will look at needs and strategies of strengthening and stabilization. Why do we need to strengthen and stabilize the structures, and also we will look at what are the various effects of loads on different structural members or different type of loads which are acting, and then we will briefly introduce various strengthening and stabilization techniques and also some general design considerations in this lecture. The remaining 3 lectures will focus on strengthening of beams and slabs and strengthening of columns and walls, and then also we will look at how the joints and connections are or can be strengthened in the next coming 3 lectures. Now, let us look at first what is the difference between strengthening and stabilization. Strengthening is the process of adding capacity to a member or a structure of a structure. Now, one example, a widely easily recognizable example is jacketing of concrete columns to increase its axial capacity. And example of what is stabilization? It is the process of halting or preventing a particular unwanted situation from progressing. For example, if you have a crack and if you want to prevent that crack from growing, then we usually say that process by which we prevent that crack from growing is stabilization. And a good example of stabilization is grouting to stop settlement, or so that the crack which are forming due to settlement can be stopped from further growth. And also there are a lot of projects which involve both strengthening and stabilization, and sometimes people also use these 2 words synonymously. So, let us see when do structures need S and S. S and S stands for strengthening and stabilization. Now, structures need strengthening and stabilization mainly because of 4 reasons. This slide covers 2 of those reasons, and the next slide will cover the remaining 2. So, the first one is fault in the design, then damage due to accidents, and then material deterioration and increase in demand. So, let me go back to the previous slide. So, let us first look at design faults and damage due to accidents. So, design fault, lower or poor performance before even the structure is taken into service. So, let us first you look at this graph here or the chart where you have time on the abscissa and the performance level on the ordinate. And so, in the first point, which is design fault, we are talking here. So, if we find the blue line is the design minimum or the minimum performance which is expected from the structure, and if we find that there is a faulty design even before the structure is put in service, then we have to do something so that the performance level can be enhanced or strengthened, so that the performance level can be enhanced and brought to a point which is above the blue line or above the minimum expected performance level. So, that is indicated by this first arrow here, Then and why this faulty design happens? One more reason is that the maybe sometimes people do not consider the long term effects. For example, creep or shrinkage, fatigue, etc. The problems because of this will show up or start manifesting not necessarily in the very first week or so, but maybe after some time, maybe sometimes even months also. And in case of fatigue, it might come many years later. And chloride ingress, carbonation, corrosion, sulfate, all these deterioration mechanisms also can play a role or can be counted as a design fault. And when I say that the design fault, I mean not only the structural design fault, but also the durability based design fault, or because of not considering some of the material parameters, what can that do to the structural properties or structural behavior of the system. The second point is damage due to accidents. So, first we covered design fault, second is damage due to accidents. And when I say accident, this is something which we do not really expect, but happens. So, collision or overload, typically vehicle accidents. If you are talking about a bridge, there are many cases where the bridge columns are hit by vehicles, incoming vehicles, or even sometimes you might see that the girders, if you have an overpass, there you will see that the girders are hit laterally by the vehicle coming, if the height of the vehicle is more than what is allowed, but even though they are not expected, but it happens in some cases. And then natural hazards, flood, wind, etc., all these will also can lead to an impact load or additional load to the structure. Now, let us look at the next point, which is material deterioration. Typically, these are associated with the long term loads, and when I say long term load, it is both structural and environmental loads. And also accidents come into the picture, the accidents which lead to degradation of the property of the material. For example, fire or blast load, if you have, these might induce some micro cracks in the concrete system, and that might affect the overall behavior or the material properties of the concrete. And then so that is shown here in this sketch by a green curve which kind of slowly degrades, or in other words the performance level is slowly degrading and then going below the design minimum. And at one point of time we go for enhancement, which is indicated by the green arrow vertical, and then we raise the performance level to a point above the design minimum. Now, increase in demand is the fourth point, okay, this one. Increase in demand is the fourth point shown here on the right end, right here. And what are the typical scenario where there is a increase in the demand? First one we can think of as seismic or any other excessive loading. Typically, if you go for a repair of a structure which was built before the seismic code revision in 2003. So, if you go to repair a structure which was designed and built before that, and now if you go and repair, you will have to actually meet the new design condition or criteria. So, that will give you end up in having or in other words we can call it as a retrofitting process. And other case is change in design code requirement, already mentioned. Then the modification of structural systems. Maybe some structures they were not meant for the change in the loads which are being experienced by the structure because of a change in the functionality of the building or because of a change in the structural systems itself. So, those are these 2 points here. So, these are the major reasons like seismic or any other loading changes in the loading conditions or change in the codal requirement or modification of the structural system, and also modification in the load pattern because of the change in the functionality of the whatever the purpose the structure is being used for, or change in the functionality. And in such cases also we go for something called retrofitting, which I will cover later what is the difference in these terminologies. But so that is the fourth arrow which you see on the right end. So, again you have a new minimum performance criteria, and so you have to maintain the structure at a performance level which is more than the new minimum. Now, what are the type of upgradations which we talk about? Now, first maintenance, repair, restoration and retrofitting. So, we will talk about these four when they come into action and what is the difference between these three. Similar like very similar to the previous slide, which we also are looking at here, time versus performance level. And let us first look at the red curve, which is how the structure would behave if there is no maintenance. Okay. So, you can see that the performance level keep going down or keep decreasing as a function of time. Now, maybe there is also if we perform some maintenance activity, then I am talking about this point here, then from that red curve there is a blue vertical arrow, that kind of during that maintenance activity the performance level is slightly enhanced, that is we are here, and then the structure will follow the dotted or dashed line, dash curve, and that is basically aging with maintenance and repair. One more possibility which will happen is, let us say if your structure is either maintained or without maintenance, if there is an accident, then the performance level decreases significantly at one point of time, immediate reduction in the performance level, and then there may be, even if accident happens, there may be some time period during which you may not do anything, you may not really repair the structure immediately. So, that is this time lag which we are talking here, and then you repair the structure and then bring back the performance level to a higher level, not necessarily to the original requirement. So, that is when we call repair, or typically these are all cosmetic repairs, and then the structure experiences further degradation in the property, and at one point of time the safety level might be very low or something. So, we tend to decide to restore the structure to its original performance level or originally expected performance level or the original requirement. So, you get the performance level to that point. Then if there is another reason for retrofitting to increase the capacity or performance of this performance level to a point which is more than the original requirement, then we go for this arrow here, or we enhance the strength further or behave the properties further, so that you can get higher capacity, and that is when we call retrofitting. So, basically you start with original requirement, if you perform some maintenance and some repair, you might, and then restoration to reach to the original level again, and then if there is a code changes or functionality changes or load conditions are increasing, then you go for a new requirement which is higher than the original requirement, and in such case we call retrofitting. So, I think just these four words are very important to know, and then how different they are, it is very important. So, we are talking about maintenance, repair, restoration and retrofitting. So, structures must be upgraded to meet the performance requirement, as and when it changes, it might change. Okay. Now, factors affecting the selection of strengthening and stabilization methods or techniques. So, first thing is magnitude of enhancement, how much enhancement is required. Okay. So, that depends on the original design, original requirement, and what is the current strength of the system, and what is the retrofitting action which is expected, or what is the new requirement. So, this will decide how much is the magnitude of the enhancement required. Now, the effect of strengthening on the stiffness of the systems and redistributed loads, stiffness of the system and redistributed loads on to the other members, that is also very important factor which need to be considered while selecting a stabilization or a strengthening method. Now, excessive strengthening of select members may change the load path or the stress flow, and hence it may not always be a good idea. In general, it might, you might feel that it is good, but not necessarily always. For example, if you are putting too much of steel reinforcement than what is required, then you might actually convert an under reinforced structure system to a over reinforced structural system, which is not a good idea. So, we must think when also when we the point which I was really mentioning is sometimes there is a tendency for the on site personnel to just change the type of reinforcement from a lower grades to a higher grade based on the availability without really consulting the structural engineers. These things happen. So, it is very important to make sure that such things are not happening, and whatever is the grade of the steel which is recommended by the engineers, that must be used, and if in case you want to change it, it should be checked again for the brittleness and the all the structural behavioral aspects. Now, size of repair project and cost effectiveness, that is also something very important. Special materials, systems and methods may be less cost effective on smaller repair projects. So, some technique which might work very well and very cost effective effectively for a long for a larger project may not be the best possible repair methodology or the repair system for a small project. So, for the specific project you are talking about, you have to analyze how is the cost effectiveness. But at the same time, when you talk about cost effectiveness, it is not the cost effective, the capital effectiveness of the capital investment, but what we have to, when I say capital here, it is for the repair, not the original construction. What we need to look at is what is the impact of that on the residual life cycle cost, residual life cycle cost. So, whatever happened, we can't do anything about it, but at least for the rest of the life of the structure, we can think about going for a best repair methodology, which will give you give you the minimum life cycle cost. Now, environmental conditions are also very important to consider. For example, if you look at high temperature or even humidity, humidity is another important aspect, temperature, humidity, and we have to look at is, for example, if you are talking about adhesive which is used for a repair procedure, that adhesive should work even at high temperature or whatever is the temperature condition prevailing and whatever is the moisture condition which is prevailing, it should work in that condition. So, the selection of materials should definitely be depending on the environmental conditions. And if you have a corrosive chemical environment, for example, it is if you are talking about repair of a chemical plant in a structure in a chemical plant. So, what are the fumes of chemicals around must be considered while deciding on the type of material which will be used, materials and systems. So, if you are having let us say a very corrosive environment, and if you are having repair systems which have which have exposed steel elements, then that may not be a good idea to go for. You will tend to have more frequent repairs. So, all this must be looked through, so that we will have minimum repair, maximum life for the repair which we are doing, and at the same time cost effectiveness. And when I say cost effectiveness, what I am meaning is residual life cycle cost, not just the one time investment. Now, more factors which affect the selection of stabilization and strengthening techniques: properties of the repair material in place and its integrity with the substrate. The bond is very important. How compatible this repair material is with the long term is with the existing or the substrate material. So, compatibility, and not only the short term compatibility, but also the long term compatibility for whatever life the structure need to last. So, for that entire time period how compatible the repair material and the existing or the substrate will be, and typically shrinkage stresses, creep and all that will lead to bond failure which need to be thought through. Now, dimensional or clearance constraints, feasibility of section enlargement, if this is a relatively simple procedure maybe, but you have to think what its impact on the available space, whether you can really afford to lose such spaces or not, or you should go for a more sophisticated or another technique which might, I will explain all those techniques. So, I do not want to introduce those techniques right now, but depending on the different type of techniques we use, each technique has its own advantages and disadvantages. So, we have to look at what technique is the best suitable for the particular problem which you have at hand. Now, aesthetics will also play a role, because if you go for section enlargement, means increasing, one example is increasing the size of a column or increasing the cross section of a beam. So, they might influence the aesthetics of the structure. So, that is something very important to look through or to look at. Now, accessibility and feasibility of the work. So, all the repair techniques may not be very easy to to implement at every every locations on a particular structure. So, you have to see for like if you are talking about a high rise building, something which can be done very easily on a ground floor level may not be that easy to do on a wall element which is at a particular height. So, accessibility and feasibility are very, very important to think through before deciding the type of repair work, before deciding the technique to be used or strengthening technique, and also the time taken for the repair work or the strengthening work, that is also very important. Fast track completion, nowadays everything we want to be done very fast, and also the lightweight and high performance materials are preferred. Why? Because if you go for lightweight and high performance, typically the chances are that you will still get a not much changes in the shape or size of the structure, and so you will not even know that a repair was done if it is a high performance material. Most often case by case it differs, but in general we can say, and at the same time when you go for lightweight materials, you will not add more weight to the structure. So, in other words, the dead load of the structure will still remain more or less similar, not much changes might happen. And high performance means again durability is something which is thought through, and also structural performance. Then safety, very, very important, and not only for the structure, safety, when we say it should be for safety for construction workers, whoever is the users and the structure. So, workers who actually perform the repair work, how safe they are is also very important to think through, and after the work is over, then the users of that structure, how safe they would be. You do not want, and if after a repair, after some time things again start falling, you do not want those things. So, all that is important. Now, let us look at what are the various type of loads which act on the structural members. So, here you can see 3 letters mainly T, C and S. T stands for tensile stress and S stands for shear stress, blue text, and the compressive stress is C. So, if you are talking about, let us say, this particular structural system, where you have here you can see that is like a cantilever section, where on the top side you have a tensile stress, and at the bottom side bottom portion is experiencing compressive stress, and right here near the support here you have shear stress. So, like that different type of stresses are acting at different parts of the structural system. why this is important is it is very important for us to know what type of stresses are acting and which will help us to understand the failure mechanism, and which will then help us to understand or to suggest a more suitable repair or strengthening technique. So, understanding how the what type of stresses are acting where is very, very important, so that we can really come up with a a strengthening technique which is very useful, strengthening technique which will really work. And at the same time, if we know that, let us say for example, if we know that a particular portion of a member will only experience tensile stresses, then if a particular portion of a member will only experience compressive stress, in that portion you do not need to actually provide something which is designed for taking tensile loads. So, this way if we can actually optimize the amount of repair material used and the amount of repair work which is being done, instead of just doing everything everywhere, that will add to the cost of work also. So, this kind of optimization will help in saving money and material. So, you can really have a sustainable approach, especially these are important when we talk about very large structural repair, very large repairs. Okay. I am not saying that for the small repair you do not need to think about it, but that is up to your choice, but on large projects it becomes much more important to think about such things, so that you can save money and material and also time. Now, loads acting on continuous spans. If you are talking about a continuous span like what is shown in the sketch on the left side, you can see continuous load is acting. So, the deflected shape is kind of shown here. Okay. Now, because of this kind of load which is acting and the type of the structure, the continuous structure, continuous span, you can see that the crack at the top because of the negative moment, and then cracking here and cracking here. So, there is a typical pattern, these are not anything new which you do not know, but just thought of refresh your memory on all these things. Now, this type of cracks, so we know that okay, what is the reason for that type of crack, and then address or come up with a strengthening technique. Now, reversal in deflections and vibrations can also happen. For example, on the right side the sketch, the graph is showing that on the abscissa you have the distance of vehicle from point A is here, and what is the deflection at point B, that is this graph is indicating the deflection at point B when the vehicle the point B, when A to B is the or when the vehicle is at any point, So, now here let me just restate this. So, here the distance of the abscissa indicates the distance of vehicle from point A, that is point A is here. Okay. Now, as the vehicle is moving towards the point B and then past point B, so the vehicle is moving from this point to this point right here, so until the graph ends. So, you can see that the type of load which is experienced by the material at point B is different. Initially, if you say it is compression and then it becomes tension, let us say looking at the bottom fiber of the girder. So, initially it might be compression, then tension, and then compression, tension, compression, and then it fades away as the vehicle is very far away from the point B, then there is no much load acting. And also we have to think about static loads and dynamic static and dynamic deflections, because based on this these needs to be considered to decide on the property of the material which have to be used and the strengthening technique. Now, loads acting on continuous spans. So, we just a little bit zooming in on what on the sketch which was shown in the previous slide. So, you can see here these are the flexural cracks because of the negative bending moment, and these are the flexural cracks because of the positive bending moment like this here, and then similar negative bending moment cracks, and then we also have shear cracks, combined flexure shear cracks here. So, these are different type of cracks, and based on the type of cracks visible, we can decide and we can identify what is the problem or why the crack is happening, and so what type of resistance need to be enhanced, okay, at various points on the structural system. For example, looking at the bottom sketch, if you have a crack, which goes like this, if I want to handle this problem, I have to provide a vertical reinforcement. If I have to handle this crack, then I have to provide a horizontal reinforcement. So, we can decide by looking at manifestations of crack, how to handle or how to address those issues. Now, loads acting on a cantilever member. Again, if you see cracks on the top portion of the cantilever near the support, we know that what the reason for that, because it is a flexure crack and due to the negative bending moment acting in that region. Now, what is the problem with this? If you zoom in, and if you, let us say, imagine you have reinforcement which goes like this, okay. Imagine you have reinforcement at the top portion, and if they are going through the crack, the zoomed in version is shown on the right side. You can see that reinforcements are actually exposed now, or the and because of this crack. So, if moisture or anything can easily go through these cracks and attack the steel rebars. So, one thing is they must be, the reinforcing steel must be located in the upper portion to carry the tension load. Why I mentioned this here is, I have heard many cases where without really understanding how the load path is, or sometimes it is also that the mistakes are done at the site, may not be based on the structural drawing, but at the site. Structural drawing things might be good, but at the site people make mistakes, and where there need to be a tension reinforcement, they do not provide the tension reinforcement, instead that goes to the bottom surface or bottom location. So, all these can happen, and then will help us in understanding the problem and then address the issue. Anyway, point is, steel is good for tension, or it is meant for taking tension. So, wherever tensile loads are acting, that is where you have to provide steel, and not in the other places. I mean, unless the load reversal is not considered, that is a different story. Now, loads acting on slab or beam to column joints. Now, volume change might be possible when there are changes in temperature from one point on the element to the other point on the element, or if there is an overall change in the temperature also, but this might lead to differential stress, lead to generation of stresses at various point on the structural members. And also elastic shortening can lead to some stresses, and stresses on the elastic shortening. Because of the elastic shortening, it might pull some other member. So, because of post tensioning forces, so you have to look at how the different elements are interacting each other also. Now, settlement or ground motion is another thing which lead to stresses. So, let us see all these how through these sketches over here. Now, on the top right, you see a slab and a beam and a column joint, and now I am looking here, this sketch here. So, you can see that if there is a horizontal force, let us say take an example of temperature variation. Let us say the element over here is expanding for some reason, and it is pushing the the whole column towards the left side. If that is happening, so if it is expanding, that can push the column to the left side, which might eventually lead to some cracking on this portion of the column, and maybe also here depending on how the stress levels are. But you can see on which side of the column the cracks are and where they are. So, these all can help us in identifying the root cause. Now, and also there may be a possibility of shear cracks, diagonal shear cracks in a beam column joint because of the heavy load or some movement in the ground. For example, in this case, assume that the other columns in this structure are actually settling, which might induce a downward force on the girders here. So, eventually leading to shear crack. And also there are possibilities of punching shear, as you can see here in this sketch. Let me just erase these. Okay. Punching shear here, which will lead to cracks like this, you can see on the picture on the left side. So, there are different type of loads acting at the joints between a slab and a column, or between a beam and a column, and we have to identify what type of loads are acting, and based on the manifestation of the type of cracks, we can based on the analysis of the type of cracks, we can identify what is the reason for it. And if you are looking at just a column, what is the type of loads acting on a column? Elastic shortening, definitely, because it is under axial compression, and creep shortening, which is an effect of a long term behavior, and drying shrinkage also. So, especially when you talk about large columns, you can have very significant problems because of creep and drying shrinkage, and elastic shortening is something which happens very immediately. So, let us go through this sketch here. So, the structure, the column is constructed, and then a load is applied, and as soon as the load is applied, whether it is pre-stress or other gravity loads, then you can expect an elastic shortening, that is elastic in nature. So, it is immediate effect, and after some time, maybe months or years, you can have creep shortening also, and drying shrinkage also will add to that. So, you can see that the delta or the change in height because of elastic shortening, and then a further reduction because of the creep or drying shrinkage shortening. Okay. So, just what will be the end effect of this when there is a shortening happening, that might also, because there is a load acting in the axial direction, that might also because of the Poisson's effect, that might lead to a lateral expansion or laterally outward forces, which might tend to crack the concrete, or in the reinforcement also might tend to bulge out, and which will push the concrete cover. So, that is kind of demonstrated in this picture here. So, this is something which is possible if you overload the concrete element. Or the type of cracks, here again we can very clearly say that whether this is due to an excessive overloading or due to a lateral load which is acting. So, that is where these understandings are very important, so that you can design for those forces. Now, if you are talking about a post tension member, initial pre-stress loss, I mean maybe we can think about seating loss as one example. Strands are tensioned and compression in concrete. Concrete experiences compression. So, this tension. So, this whole concrete here is under compression and the strand is in tension. So, first thing which happens immediately, in the previous slide we talked about a column, here we are talking about a girder. So, immediately what happens? Elastic shortening. As soon as the pre-stress is applied, the concrete experiences a shortening. So, the elastic shortening happens. At that process, it might induce, like these columns are also pulled towards each other. Because of this, it is possible that you can develop some cracks on the outside surface of the columns. Now, if it is continuing for long term, then again creep, shortening and drying shrinkage might continue to happen, and hence you can notice here the shortening is now more. Here you can see here. Okay, so, this much is the extra shortening which happened, and here also this much is the extra shortening which happened. So, this is additional shortening due to the long term effects such as creep and drying shrinkage. And pre-stress losses can also happen, because when there is a creep and shrinkage happening, the length of the strand is also decreasing. When the length of the strand is decreasing, that means that that strand will not provide there will be a loss in pre-stress. So, all these factors will have to be considered, and then the type of cracks can tell us what is really happening in the structure. So, that is the idea. Okay. The whatever is the we should be able to take visual observation, we should be able to make visual observations, and from those visual observations we should be able to identify the damage mechanism or what is happening in the structure, so that we can design suitable strengthening techniques or strengthening methods. Now, more on this loads acting on post tension members. You can see here, if you are talking about a parking garage for example, usually they have very short column, it is a typical short columns, because not really a high bay structures. So, short columns, and then if you have imagine this whole roof element here is post tension, a PT slab, post tension slabs and short columns, this combination is what we are talking. Now, if the pre-stress or post tensioning is too much, then there will be a pull, I am talking about this column here, that there will be a pull to the right direction from the top, or this slab or the top is pulling the whole thing to pulling the short column to the right direction, whereas the bottom slab is pulling the short column to the left direction. Okay. So, because of this, indicated by these two black arrows. So, your direction of the pull to the right, and then short column is trying to resist that, okay, and that will lead to inclined cracks like this. Okay. Now, short column is trying to resist, but at the same time there is also a possibility that the bottom slab is pulling, this slab is pulling the short column to the left side. So, whichever reason. So, the type of cracks you can look at, what is the angle or direction of the cracks, and that will tell us which force is actually creating this crack, are the reasons for these cracks. Now, let us look at the bottom column here, bottom portion of the column. Again, the crack direction is opposite, it is going into the 45 degrees in the opposite direction, and there the reason is there is a leftward pull by this slab or that post tensioning element, and the short column is trying to resist because it is sitting on ground. Okay. So, it tries to resist, and then it leads to the inclined cracks like that. Okay. So, different type of cracks, you can see the top portion or this region is experiencing a crack in one direction, and whereas this region is experiencing a crack in the opposite direction, but both are in 45 degree angle. So, there is something to do with the shear resistance. Now, two types of strengthening designs, one is passive and then other one is active. When do the loads act on the additional components? That is based on that is how we tell whether a particular design is a passive design or an active design. Now, when you talk about passive strengthening, they are the type of repairs or strengthening elements which do not take part in the stress sharing until additional loads or live load are applied and or until acceptable levels of additional deformation occurs. So, they do not take part in the beginning, whereas the active strengthening they immediately take part. Okay. In the first case, the passive strengthening they do not take part until either the load level increases or there is a significant deformation, whereas in the active strengthening, the elements which are the strengthening elements will take part immediately after they are installed. They will take part in stress sharing, and then actually no additional deformation is acceptable in the active strengthening designs. I will show you one example of each of this. So, passive strengthening, when live load changes are anticipated. One example is dampers. Let us say if you have dampers to resist earthquake, so they actually start functioning, or magnet or rheological dampers for example, they actually start functioning when there is an earthquake. Until that moment there is no, the dampers do not really have a role. They are there, but they come into action when there is a significant load. And then upgrading of a bridge to carry heavier loads. Okay. When a bridge is now to carry heavier load, but it is not necessary that always the bridge will experience that heavier load. So, when there is the heavier load, at that time the passive strengthening elements will come into action. In the case of dampers, when there is an earthquake or when there is a heavier lateral loads or something, at that time the dampers will come into action. So, these are just examples on it is like the extreme cases, or in other words the structures are designed for the extreme cases. So, when that extreme load conditions occur, at that time these elements will come into action. Now, example is here, you can see a beam with a plate something below, okay, and a plate element below which is not pre-stressed. So, this plate element will come into action only when there is a significant deformation or a significant loading. Until then it just stays there. As opposed to that, there is an active strengthening system which immediately participate. Example is pre-stressing. Okay. So, if you have a plate element like in the bottom image, you can see a laminate, CFRP laminate here, which or any pre-stressed element. In the top one you can see a pre-stressing or external post tensioning unit which is under stress, and it takes the load as soon as it is in place. So, one example on the top is the external post tensioning, and at the bottom is external post tensioning using a laminate. Both kind of functionality is very similar. So, both will take the load as soon as they are installed. They do not wait for that excessive loading to come. In other words, they continue this start taking the loads as soon as they are installed. Yeah. Now, different methods to strengthen and stabilize structural elements and system. One is replace. First thing to do is replace all that is bad, or replace poor quality or defective. Poor quality means the material properties are poor, defective means they might have been good in the beginning, but something happened and then it got degraded. Okay. So, material by replace them by using good quality materials, and then redistribution of the loads through imposed deformation, or you allow some deformation to happen so that the stresses are not really happening the way which is harmful. So, redistribution of the loads through imposed deformation of structural system, and at the same time sometimes we can add new members which will take this additional load. And then other methodology is attaching new load bearing materials or systems to transfer, relieve or reduce the stresses. Three things. One is, if there is a stress generation somewhere, if it needs to be transferred, it need to be transferred. Okay. If it does not need to be transferred, there are some cases where we will try to relieve the stress, or have some space available so that the stress does not get transferred to the next element, like expansion joints. Another way is to reduce the stress by having a system which will distribute and then reduce the stress on the on the members. Okay. So, all these we will cover in the coming 2-3 lectures, but this idea here is just to give you an introduction. So, 3 terms to be remembered here is transfer, relieve and reduce the stresses. Now, how do we do all this? By using high quality concrete, by using reinforcing bar internally, maybe by drilling an extra hole in the concrete and then providing a bar inside, that will help, and also sometimes by thin plates or thin steel plates or non-metallic or FRP or fiber based straps and some laminates which are usually placed as an external member. They are glued to the concrete surface, and then post tensioning tendons which are external but not in direct contact. So, they are post tensioned with some anchorage points and deviator points. I will discuss all that also later. And grouting is done usually to stabilize the structure, so that there is a proper load transfer. Okay. And then joints and connections also have to be proper joints and connections which will help in transferring the load in the way which we want, or sometimes to not to transfer the load which we want. Now, enlargement of cross section, span shortening, these are all so kind of different techniques by which we can control the stresses, and that way minimize the damage on the structures. And above all, one very important thing is we must think about short term and long term loads, not only the short term loads, because even if a system works very good for a short term load condition, it might not really work for long term load conditions. And in such case, usually it is the material properties which are very, very important. You should think about how the material property can degrade over time, and make sure that the material which you use do not degrade over time. So, whatever assumptions you have on material properties at the time of construction should remain like that during the entire life of this structure. So, cracking of repair material at joint, definitely that must be prevented by providing enough time for that material to build enough strength and stability or stiffness, so that crack do not really happen. Now, different type of materials used, polymers, cement based mortar, concrete. So, you have to see which type of material is good, considering finance money also, which type of material is economically feasible and technically feasible, and then use such materials. It is not necessary that always you have to use something which is available in the market, something which is widely used. So, sometimes you will see that many places people use unnecessarily material and waste money also. So, judicious decisions have to be made, so that you can optimize both the technical aspects and at the same time the economic aspects. Now, loads during curing, this is what I just briefly mentioned earlier, how the material will behave during the curing period. So, in other words, you have to ensure that the material get cured properly and build sufficient strength and mechanical properties, so that it can actually take the load at a later time. Now, static and dynamic behavior should be looked at. If some crack is there, it might look like that crack is not growing, but it may actually be growing, or it may actually be closing and opening in case of fatigue loads. So, all these have to be thought through, and the material selection is very, very important. It is not only the structural system designs, but the materials which we use should actually take those loads also. Okay. So, I am going to summarize this lecture. We talked about the need of strengthening and stabilization. We looked at different strengthening, like the different terms like maintenance, repair, restoration and retrofitting, what is the difference between them, and also looked at different type of loads acting on structural members, and also talked about general design consideration, material consideration, while selecting a strengthening and stabilization techniques. And these are the various references which we use in this lecture. So, in the next lecture we will talk about how to go for flexural how to go for strengthening beams and slabs. Thank you.